We can find the delta H for this chemical reaction by using this table of average bond energies. The idea behind all this is that you can always find the delta H for any reaction if you have the bond energies. The delta H is going to be the total of the bonds broken, minus the total of all the bonds formed. And the reason we're subtracting the bonds formed is to make them negative, because that would represent the exothermic event of bonds being formed. Bonds being broken, we're going to leave positive because that's endothermic to break all those reactant bonds. So the bonds broken come from all the reactant bond energies. Looking at the first reactant, C3H8, I'm counting 2 carbon-to-carbon bonds, and then I'm counting 1, 2, 3, 4, 5, 6, 7, 8 C to H bonds. So if we keep up with all those bonds broken, on this one, each of these we can find from the chart, right there, is 348. And there's another 348 there. Plus each of the C to H bonds, we can see those are 413 each. So if we add up all those for the bonds broken, we would have 2 times 348 from the carbon-to-carbon bonds. I'm going to write over top of some of this stuff here. We would have 8 C to H bonds at 413 each. Then I've also got 5 of my oxygen double bonds right here, and those are 146. Those are somewhere else. Those are 495 down there on the chart. There's the O2, 495. They put that one separately, and so there's 5 of those. So I'm going to add all those together for all my total bonds broken. And that adds up to 5956.87. I'll just keep all my digits. I don't know how I got that 0.87. Oh, typo there. I had something in there beforehand. Let me do that again. 2 times 348 plus 8 times 413 plus 5 times 495. 6475. That sounds better. All right, and those are kilojoules. That's positive from breaking all those bonds. Now I'm going to get the sum, the total of the 3 CO2s. All right, so now over here on the opposite side, back to my products, I've got CO2, each one having 2 carbon to oxygen double bonds. Finding that on the list, it looks like it's 799. Plus another 799. But because there's 3 of those total, that means in my total bonds broken part over here, I'm going to have 6 of those CO bonds at 799 kilojoules each. That's because there's 2 bonds per carbon dioxide and there's 3 carbon dioxides. All right, so same idea for the H2O. The oxygen to hydrogen bond, looks like it's right here. It's 463 each. And so each one of these is 463. And there are going to be a total of 8 of them because there's 2 per water and there's 4 waters. And so that's all of my bonds formed there. So I'm going to add those up. 6 times 799 plus 8 times 463. And my calculator died as I'm making the video. So get my phone out here. All right, 6 times 799 plus 8 times 463. That's 8498. Now this total, I'm going to end up subtracting it from the red number of 6475 because all of these bonds are formed, and that's going to represent the exothermic event. Now just I'll subtract these two numbers, 6475 minus 8498. And to get my overall answer for this, the delta H for this reaction is negative 2023 kilojoules. And that's what I would find out, that the delta H for this whole reaction here, kind of out of room, is that answer, negative 2023 kilojoules. So in the end, that's how you can find the delta H for any reaction when you're given a table of bond energies or bond enthalpies. You just add up the sum total of all the reactants bond energies, and from that you're going to subtract the sum total of all the products bond energies.